Thank you very much. I will talk into the microphone. So yeah, I'm Miren. I'm going to be talking about numerical relativity with AMReX and what we've been getting up to in the UK. So first, some introduction. So who are we? I come here with a number of hats. So I'm a research software engineer in research computing services at the University of Cambridge. So I don't really have any reason specifically to be involved with this project, except I previously did a PhD in numerical relativity, so I have some scientific background as well as a kind of computational role as well. I'm involved with kind of two codes that are AMReX based or kind of moving to AMReX at the moment, AMReX. So that's GRTeclyn, and you can see some faces on the left of people involved with the GRTeclyn development and the code. MHDueT in the middle two, that's kind of a smaller collaboration, and they're in the process of porting to AMReX as well, and I'm involved with that. And the new thing I'm going to talk about, which is this lots of letters, is the UK NRCCP, which is the UK Numerical Relativity Collaborative Computational Project, and this is a grant we've got to do some, to do lots of things to form a kind of computational community, which will have long-term funding that I'll talk about at the end, and I'll talk about what my role involves with that and how that relates to the other stuff I'm going to talk about. So there, some faces on the wall. So first of all, what is numerical relativity? And it's a good thing I've muted my laptop because that video has some horrible music otherwise. So numerical relativity is an area of research that uses numerical methods to solve the Einstein equation. And so for those that may not have come across it, or going back to kind of university, college level physics, the Einstein equation roughly says that curvature plus this horrible term that Einstein had to add later on when he forgot about it, the cosmological constant. So the curvature, the Einstein tensor, which is some measure of the curvature plus this extra term, is proportional to the energy momentum tensor, which is kind of some tensor which measures the content of matter in your space-time. So this equation in this nice, very pretty looking tensorial form is unfortunately not great for numerical evolution, so we had to recast these equations, and that actually was a kind of a long research process and took many decades to find the correct form that was good for numerical evolution. So we recast these equations to a set of coupled nonlinear hyperbolic PDEs. We also have kind of elliptic constraint equations, and typically in numerical relativity, most of us and we only solve those elliptic constraint equations on the initial data, and then we monitor those quantities over the evolution. And obviously, if they're getting too big, then maybe we need to increase the resolution, or our simulation is going unstable, or something like that. But there are some. We also impose some kind of damping terms to kind of damp out violations to those constraints as well. But we don't explicitly enforce it at every single time step. So what kind of problems do we look at in numerical relativity? So you can see in the video, that's kind of a visualization of kind of a binary black hole merger, and this is actually, I think, supposed to be a visualization of the first binary black hole merger, the simulation of the first binary black hole merger that the LIGO detectors detected in 2015. So common problems include compact object binaries. These are the kind of most astrophysically relevant problems. So black holes, as you can see in the video up there, neutron stars, another kind of black holes and neutron stars are the most common, but also, and particularly the research groups that I'm working with are interested in more exotic objects. So I've looked at things such as boson stars, which are stars made of kind of scalar matter. But in addition to that, numerical relativity is not only used for those kind of most astrophysically relevant problems, it's also used to study cosmological problems, kind of inflation in space-time, and other things that I probably know a bit less about because I haven't been involved with that so much. But in addition to that, we use numerical relativity to kind of perform numerical experiments for fundamental physics. So if we have a new fundamental theory, then we can see how that affects problems in kind of gravitational scales. So one of the things we're typically interested in, and I've already kind of alluded to it by the kind of LIGO detection that I mentioned for the video at the top, is gravitational waves. So this is the thing we're kind of typically measuring in a simulation. We're interested in the gravitational waves emitted in a simulation, and that's kind of particularly relevant in the kind of astrophysical kind of compact binary case, the binary black hole, the binary neutron star, or the kind of mixed binary black hole neutron star. And as you can see on the bottom right, I've got a kind of, this is a picture of a simulation I did a long time ago, of the kind of measure of the strain of gravitational wave from an equal mass binary black hole merger, and you can kind of see it in spiraling here, and then it kind of merges, and then it rings down, and then it kind of settles into a, which you probably saw earlier in the video if you were, I don't know, looking at the video rather than paying attention to me. So what are the kind of common methods in numerical relativity? So I've kind of highlighted the ones that are kind of most relevant to what we use, but these are by no means the kind of only methods that are used in numerical relativity. So for the discretization, we just use finite differences. So one of the codes I'm going to talk about, GRTeclyn uses, is a cell-centered code. The MHDueT is kind of more node-centered. But obviously other codes use finite volume. That's more common for kind of magnetohydrodynamics. Spectral methods are very common, and they tend to get higher accuracy if being a lot more of a pain to deal with. And then discontinuous Galerkin methods, which I know very little about, are coming more common as well. So within kind of finite difference mesh refinement, block-structured adaptive mesh refinement like AMReX is not the only method. There are also other frameworks that use kind of octree adaptive mesh refinement. And even kind of older codes that use block-structured adaptive mesh refinement, I mean, maybe adaptive was too strong a statement, because what they actually did was kind of a moving boxes approach where they kind of centered kind of boxes around the black holes, and then they tracked the centers, and then they just moved the boxes around. It wasn't very adaptive in the sense that it was looking at errors or using some other kind of more complicated criterion. But, libraries like AMReX, we need for kind of more adaptive mesh refinement for more exotic spacetimes and more weird matter that's going on kind of than the more conventional binary black hole case. We typically use the method of lines for time integration. So we use fourth order. So we use, and that's quite common across kind of the codes that are similar to ours, we use fourth order Runge-Kutta time integration. Fourth or sixth order spatial discretization. You might wonder, well, why bother with sixth order? You're already only getting fourth order from the time integration. And actually, we find that makes a significant difference for kind of long black hole binary in spirals. So long simulations, that helps with our accuracy. We use a thing called, I don't think it's common outside of numerical relativity. We use Christ oligo dissipation to kind of dissipate noise from the boundaries of refined levels. The boundary conditions we use, so a typical kind of common condition, which I'm not sure is super common outside of numerical relativity, is kind of the Sommerfeld radiation condition. And this kind of ensures kind of no incoming radiation from infinity, just only outgoing radiation. So we allow kind of waves to propagate outwards freely, well, linear waves, and our problems are nonlinear. So there is still noise we introduce from that. It's an approximation, but it usually works well if we set our boundaries far enough away. We also use kind of symmetric, and if we have a binary black hole merger and they're just inspiraling in the kind of same equatorial plane, then we can impose kind of symmetry on that. We don't need to evolve the whole 3D domain. We also used extrapolating conditions as well. And some of the other codes, we don't do this, but some of the other codes use kind of multi-patch approaches. So they have, the standard kind of, cuboid domain, and then they have like another kind of, maybe a cubed sphere domain kind of surrounding their cube, with kind of imposing conditions allowing kind of radiation, kind of more of an extension of the kind of Sommerfeld radiation condition. But we don't do this yet, and I'm not sure. I think that is quite finicky and introduces lots of problems as well. So there's many numerical relativity codes. I won't go through all of them. There's kind of three main classes. There's the kind of octree adaptive mesh refinement. There's the spectral and the kind of pseudospectral and the discontinuous Galerkin codes. And then there's a block-structured adaptive mesh refinement, of which you can see there's many more. Kind of broadly, the spectral ones are the ones that do kind of the most accurate simulations for gravitational wave detection for LIGO and Virgo. But those codes are quite difficult to set up, and they're very difficult to adapt to new problems because they're so big and complicated. So they tend to kind of restrict to just those kind of astrophysical cases. The block-structured adaptive mesh refinement codes are definitely more nimble. They're more able to adapt to problems quicker, and they're able to explore kind of new, kind of exotic spacetimes and things like that. There's a long list of codes here. The main ones that I've kind of indicated with this kind of dagger is that these are codes that are kind of transitioning to or developing kind of AMReX frameworks. Transitioning and developing support for using AMReX as their kind of AMR backend. So one of the kind of big ones is definitely the kind of the Einstein toolkit, which is based on the Cactus framework. And there's many codes that use this, but it's a framework, so there's lots of different codes. And they're transitioning to AMReX using a thing which they're calling GRTeclyn. But that's been a kind of long and complicated project because it's a huge kind of framework that there's lots of things to do. I'm not involved with that, but I am involved with kind of MHDueT, which I mentioned on the first slide, and GRTeclyn is the one I've been involved with for the longest, for the last couple of years. And GRTeclyn is a port of the previous code, GRChombo, and MHDueT is an auto-generated code which is generated using this framework, which is called the Symfony framework. Yeah, so I'm going to talk a little bit about GRTeclyn. It's on this slide. So GRTeclyn is an in-development port of GRChombo, previously built on the Chombo libraries, adapted mesh-refinement libraries to AMReX. The reason we chose Teclyn is because Teclyn is Welsh for tool, and we've kind of decided to stick all of the codes in that collaboration. The GRTL collaboration, GR tool, is we're naming it as GR for General Relativity, and then some word for tool in some language. So there are some Eastern European languages that I struggle to pronounce, but thankfully this one is Welsh. It's close enough. I can definitely pronounce it. So it's an AMR based as opposed to being AMR core based code in AMReX. It's cell centered, and that's kind of for historical reasons because we came from Chombo where things were cell centered. Perhaps if we were starting from scratch, maybe kind of node centered would make more sense because we use finite differences. We don't use finite volume, so the value at the center of the cell is not the average of the kind of the volume of the cell, but rather just the value at the center of the cell. So actually, as a result of that, Wei Chun was very helpful, and he helped us develop some new kind of interpolators that we use. This cell Cortex interpolator, which is designed for fourth order cell-centered data. And he also developed a kind of fourth order interpolation from fine to coarse, and we use this in GRTeclyn. The video's kind of stopped, but that was a video kind of comparison between GRTeclyn and GRChombo of kind of some of a binary black hole merger. I'll just play it again whilst you're listening to me. We use fourth order and Runge-Kutta time integration, and this was another thing that was added to AMReX when we were porting GRChombo to GRTeclyn. So since then we now have Runge-Kutta time integration in AMReX. We currently just have one example, which is the binary black hole example, which you can see kind of simulated. Kind of this is a measure of the kind of the strength of the gravitational fields, and you can see the black holes in spiraling and merging. And that just evolves black hole binaries. And the idea behind GRTeclyn and the previous code GRChombo is designed to be flexible and easy to adapt to new problems. And here are some benchmarks of we just ran the code on various different GPUs and one CPU. It's only one GPU in each case, the one MPI rank, except the Intel PVC, the Xeon Data Center or Data Center Max, GPU Max, and that's because of the structure we use two MPI processors. And then on the Intel Sapphire Rapid CPU, we used all of the cores, but we used 4 OpenMP threads, and then the rest was distributed with MPI. But yeah, we're pretty pleased with the performance we're getting with and this benchmark's quite old. I think it's from early last year, so it should probably be updated. So what's some recent developments? So one of the things I've been involved with is kind of the puncture tracking. This allows us to track the center of the black holes. This is our first use of AMRex's particle infrastructure. We had not used particles before that. Perhaps a bit overkill because we only have 2 black holes typically in a simulation, so we only have 2 punctures. But this is a good experience for kind of getting started with particles, and I'll be talking a little bit more about particles in a minute. So one of our recent kind of developments, and Wei Chun was involved with this as well, was kind of we have very high register pressure from all our variables. The big tensor equation from the Einstein equation. And from GRChombo, we had kind of legacy, kind of complicated data structures in our kernels that evaluated the right-hand side. So we kind of, Wei Chun suggested, refactoring this might help with the register pressure, and it was a huge speed up. So we had a hackathon which was kind of porting codes to AMD MI300A with support from AMD, and that was basically all they did was they kind of refactored these loops, and they had a massive speed up, 2x speed up in the right-hand side, which led to kind of 40, and obviously that's a dominant contribution to the wall time. So it's 40% overall contribution, 40% overall faster than before. Actually, 40% is maybe 40% faster, yeah. And we're currently working on adding support for basic matter because currently the black holes is just a vacuum spacetime. Now I'll talk a little about MHDueT, which I've been involved with for the past year. So it's a code that's generated using the Symfony infrastructure. It previously used the kind of SAMRAI adaptive mesh-refinement library. Unlike GRTeclyn, it's AMR core-based, so they do a lot of the things themselves. It's mostly node-centered. They have their own custom interpolation routines that use the fifth-order polynomial interpolation from coarse to fine. They have their own kind of Runge to time integration that they developed to ensure the accuracy that they want. They do magnetohydrodynamics, including high-resolution shock capturing with this we know reconstruction, which I don't know very much about. And they allow they use HDF5 tabulated input for their kind of an arbitrary equation of state. And this code currently can simulate lots of different binaries. It can do binaries of boson stars, neutron stars, black holes, and obviously mixed binaries and that kind of thing. And it's also generated using the Symfony infrastructure. I think as a developer, I'm not the biggest fan of the kind of auto-generated nature of this code, but I think the idea is meant to be kind of simpler for kind of the scientific user, which may have less programming experience. And this is a picture of some kind of jets from some old MHDueT simulation of kind of neutron stars. So what are some kind of recent developments? So what I've been involved with, so one of the things we found was that when the code moved to running on GPUs, there was some instability that they weren't able to solve, and the kind of addition of nodal syncing really helped to kind of to save that. We refactored the kind of boundary conditions, and it was a 3000x speed up. I mean, it was really doing badly. They didn't use that boundary condition because it was too slow, so that was helpful. And we refactored some of their reductions to use AMReX's parallel reduction, par reduce, to kind of rather than custom code, because it's now GPU offloaded and working much better. And we linking back to another thing in the kind of HPSF is we kind of switched the dependency build scripts and custom shell scripts to kind of SPAC environments as well. Yeah, so what's kind of the future work? So I mentioned particles. So one of the things we're kind of looking at is kind of, we want to extend the diagnostic particles. We want to use particles for diagnostics. So I mentioned we want to do gravitational wave extraction, which we typically do on coordinate spheres. We want to use it for kind of tracking where the apparent horizon is. This is some measure of the kind of boundary of black holes. We want to kind of look at the matter flux around coordinate spheres, but we're also interested in kind of actual physical particles as well to model kind of collisionless dark matter particles in GRTeclyn and neutrino transport in MHDueT, and also use like it's common in fluid codes to use kind of geodesic tracers to kind of investigate the behavior of free moving particles around compact objects. And I mentioned the UKNR CCP. So this is a grant that's funding my travel here, and the reason that I'm here. And this is the kind of collaborative computational project. It's from the kind of, it's actually the logo in the top left, which is quite small, the Computational Science Center for Research Communities, which somehow they've abbreviated to COSEC, but there you go. And this is the idea behind this is kind of just a roadmap grant. It's only a 2-year grant to kind of to work out the kind of what we need to do to develop this kind of collaborative computational community, which will provide long-term funding for the community to work together. And as part of this kind of technical branch of this grant, we are benchmarking the performance of existing numerical relativity codes, including the two I mentioned, but other codes that are in use, and we can compare them and see how they perform on different hardware and see what their capabilities are. And this is the work that I'll be doing, kind of identifying opportunities to make data formats more interoperable to allow different codes to read in and kind of compare data between them, and also developing kind of common analysis tools. So at the moment, a lot of kind of codes do their own development of analysis tools. And it's all kind of, it would be much better if it was kind of unified and everyone could do the same thing together. I think that's it. Thank you very much.
We have time for like a quick question. Do you want to be setting up, Zaria? You're the next speaker.
Yeah, I'll disconnect mine.
Any questions?
You mentioned the MHDueT.
MHDueT?
Yeah. So for the hydrodynamics, do you still use the finite difference method, or?
This is a good question. I was trying to understand this. To be honest, this is not something I have been involved with. I think they still do, but then they do some other things. They add some. I'm not really sure. They do some weird. I was actually going to ask them about this. They do some weird kind of. They do flux conservation and this kind of thing, but they still think of it as finite difference. I'm not really sure. I'm a bit confused myself, but probably a question for, I can ask them if you want to.